Thank you. I'm very happy to present this talk today. So before giving the title of the talk, I'd like to question the activity we all have here around data science. And I mean, is it still science first? I don't know. For me, science is, let's say, an interesting blend between creativity, technicity, and usefulness. And from my point of view, it's like a triangle. So let's say we have technicity here, usefulness, and creativity. So here we have creativity is poetry is pure creativity, I guess. Technicity is like New Rips paper, I guess. And usefulness is like, you know, EDF or RTE, you know, bringing electricity to our homes. So maybe you have, you know, engineers, maybe they are in this part of the corner at EDF, and data scientists publishing at New Rips are maybe on this side of the corner, and maybe poets and artists are in this side. So I think we are too much on this one, and maybe we should move around this part. We need more creativity and maybe think about the usefulness. So actually I borrowed this quote. I just changed the word in red. So they should stop training data scientists now. It's just completely obvious within 5 years that deep learning is going to do better than data scientists. And it might take 10 years, but we've got plenty of data scientists already. So I said this today, and who knows what happens. But actually, I've stolen this quote from a Nobel Prize. So Jeff Hinton, before he became a Nobel Prize, maybe there's some causality, by the way, being provocative and you know, having this kind of stupid statement maybe can, you know, who knows where it can lead me. Maybe I will become a Nobel Prize in economics, you know, in a field I have nothing to do, you know. So he said this in 2016, and actually we have some kind of answer today of what happened, you know, a few years later. And the answer came from a team of researchers in behavioral economics at MIT. So I will tell you in the last slide, you know, what is the answer to this quote as far as radiologists are concerned and their interaction with AI tools. The talk will not be very much technical, but there will be some technical part that will be devoted to describing the uncertainty out of distribution for deep learning. But of course, we can put a wider perspective on this question, like, you know, what can we say using data science in general? So I'm being provocative and describe, you know, roughly what is a research cycle in data science. So first we have to focus on a hot topic. What is a hot topic? It's something on which prominent researchers over the world, especially in the US, ideally in, you know, in good university, good American universities, or in private research labs in big tech companies. So this should drive the choice of the topic. Then we should make an incremental, but not too creative. Remember, we have to stay in this part of the triangle, but promising though, and just change a bit their model, their algorithm, the performance metric, you know, these are the main ingredients. And then we run, in France especially, with much less resources than our colleagues in the US have to run their experiment. And we test this novel method on the usual benchmark data sets until we observe some improvement with respect to the chosen metric, okay, over a test set. And in addition, if we manage to have theoretical results, then we are good for the best journal or conference. Okay. If it looks technical enough, that's fine. I mean, it's my experience of, living in this community. I had papers that were creative and useful, but they were not technical enough. So the reviewers said, it's not technical, it's not a good paper. It happens. So it's real life. But I think this cycle raises some question about what is the meaning of that. The first question is that we provide generalization error bounds, but what can we expect from this? There are theoretical results, mathematical theorems. So what kind of guarantees they provide? That's the first question, quite technical. The second question is, when we confront ourselves to these academic benchmarks, what is the longevity of the data sets? At some point, maybe we cannot go beyond, the accuracy, fairness metrics, whatever we choose as a criterion. Maybe we reach, the limit. So what is the life cycle of the data sets? And interestingly, we can also give some kind of theoretical insight on this question. And then the third question, maybe is philosophical to you, but for me it's scientific, and that's the kind of research I would like to develop in the next 10 years, which is how much data science informs us on physical systems, on biological systems. What does it bring to knowledge, to science in general? I mean, beyond the world of data science. And I think it has some role to play, but it requires probably a different mindset. So first, let me discuss the first question, the first issue about bounds and the limitations. So what I will say here is probably known for most of you. So just classical notations, supervised learning with binary labels, +1, -1, binary decisions, H taken in a hypothesis space H, binary loss functions, true error, which is the expected value of the loss over the domain, and with respect to the joint distribution of the data, and the empirical risk of a decision rule is just the rate of misclassification if we use a binary loss with the predictor H. Okay, so we denote by L of H the true error, and L hat dn of H the empirical error. We keep track of the notation for the training data, which are denoted here dn, so we have a training sample of size n, and they're assumed to be IID, okay, of distribution P. So the generalization error bound based on Rademacher complexity, if we define the Rademacher complexity to be the complexity measure to characterize the size of the functional space H, recall this is the expectation, the conditional expectation given the training data of the supremum over H of 1 over n, sum over I, of epsilon I, H of xi, where the epsilon I are IID uniform signed variables with values +1, -1. So this is like, the more the prediction vector over a set of input vectors is correlated to a purely random noise, it means that the size of H is significantly large. And so with this kind of characterization and using concentration inequalities, we are able to provide guarantees on the true error of Hn hat, assuming Hn hat here is the empirical risk minimization. And we can give, sorry, there's a typo here, it's infimum of L of H on the first line. So we can give a guarantee on this excess of error in terms of true error of the estimation coming out of the learning algorithm with respect to the best error in the class. This is controlled essentially by the complexity measure related to the Rademacher average, and you can either see this through an empirical quantity like the second inequality, the Rademacher average that depends on the training data, or you can consider in expectation. It becomes like a distribution dependent complexity measure. Okay, so some comments. well, concentration inequalities are important to prove this kind of results. Similar arguments, but with quite a few technical refinements, can be applied to many other situations, like margin error bounds, convex risk bounds, preference ranking risk, and so on, mostly for batch learning algorithms such as SVM, feed-forward neural networks, boosting, and so on. Now, there are other approaches to prove generalization error bounds, which do not rely on they do not assume that we have batch learning with empirical risk minimization, and they do not necessarily involve some characterization of the complexity of the class. And this includes the notion of stability that we can apply to strongly convex losses. And we can also have direct rate bounds for sequential learning type of dynamics, such as stochastic gradient descent. It's the same type of argument we have for the classical perceptron. And this works for smooth losses, but not necessarily convex losses. Okay, in all that scenarios, we have a control on this quantity L of Hn hat. So Hn hat comes from some algorithm using training data and a class of candidate predictors. And we have L of Hn hat. So this is a slight abuse of notation because actually this is the performance of Hn hat of X given the training data. Okay? So in practice, this is estimated with a test sample. This is known as the holdout method. Okay? So if we have given some data, we should put in a vault, as the guys from Stanford say in their famous book, that the test data, nobody should see it before doing this blind test on any estimation method that is used. And it is typically assumed that this test set follows the data in the test set, follow the same joint distribution as the data in the training set, and it's independent of the n. And so we have some kind of fair estimate and bias estimate of L of Hn hat with some empirical distribution that relies on the test set. And we evaluate the empirical error on this test set for Hn hat. Okay, but in practice, the data scientist performs many training sessions, and he probably selects the Hn hat depending on the previous experiments. So this creates some kinds of dependency between the displayed Hn hat and the test set. Okay, so there is some mechanism that creates this dependency and breaks the independence assumption. And this is known, and there are papers describing this mechanism. This is known as overfitting by ensembling. There's a paper by Hart and Recht in 2022 that shows this kind of bound that you can have a discrepancy between the true error and the empirical error, and this discrepancy is lower bounded by something which is like a square root of log of k divided by n, where k is the number of estimates that the data scientist has provided on the same test set. Okay? So it looks like if we have an entire community working on the same data set, some overfitting may occur on the test set. Okay? So this raises the question of the longevity of data sets. Maybe very quickly they become obsolete because we are kind of overfitting as a community, we are kind of overfitting on this data. Is that the case? Well, interestingly, not exactly. In fact, there is some underlying mechanisms that kind of prevent the worst case scenario, which was described in the work I mentioned before. And there are some assumptions about why this overfitting effect is not that strong. And among the possible explanations, there are essentially two that are commented in the literature. So one is the model similarity. Like, in fact, there's not so much diversity in the ensemble that is produced. Like the predictors that are provided by different teams, different scientists, or along an interaction with a given data set, in fact, are very similar one to the other. So maybe they improve slightly the error, and they are essentially, you know, if we look at their symmetric difference, if there are classifiers, they are very close. So this is a first idea, and this has been commented by people working on deep learning methods, talking about, you know, this flat, what's the name again? Flat valleys. Okay, so all the local optima are kind of the same. They provide the same kind of performance. And there was an alternative approach by Semenov, Arudin, and Parr about the same period in 2019 that they have a different angle on this model similarity, and essentially what they claim is that we should look for simpler models that can be interesting for topics like fairness, explainability, and that provide a better understanding and better control on machine learning techniques. So this is like a positive view on model similarity. And there is another argument, which is the leaderboard principle. So the paper goes back to work by Bloom, Avrin Bloom, and Maurice Hard in 2015. And the leaderboard principle applies to Kaggle competitions. And what I like in this paper is that they, you know, set up clearly the problem, and they define what is the leaderboard error. Like, you know, the best classifier you have ranked so far. And so the leaderboard error, given a number of estimates of your accuracy, error, whatever, is the maximum over the number of estimates of the discrepancy between the current estimate, RT, and the minimum of the true errors you have observed so far. So if you have test errors, of course, you should plug in the test error instead of the true error to have a monitoring of the leaderboard error, but still you can define this as an objective. And they introduce an algorithm that kind of filters the current estimates within some threshold compared to the previous best one. And using, you know, this, then there's some kind of counting argument along all the possible. You build some kind of tree, and you count the possibilities along this tree, and they manage to show that the leaderboard error with high probability is upper bounded by a term that goes to 0 with n in. And the rate of convergence is the following. So it's log of kn divided by n to the power 1 to 1/3. All this ratio is to the power 1/3. Okay, so so this is, let's say, a positive result. Yes?
Excuse me, is h hat the same as r, or is
what?
I don't understand the notation. So the h hat is the
hn hat I is the current, the estimate. So you have k different estimates, and at step t you have observed the error for the t first estimates. So hn hat of I is what can be obtained with, you know, different teams in a competition, for instance. Okay, so you have a ranking at each round, and you can follow you compare yourself to the best until this. So probably it depends if you allow each team to submit a new a new entry. Well, in this notation, I guess that there's every T is a new entry in the leaderboard. So you can have these kind of guarantees with what is known as the ladder algorithm. And then the second mechanism about the model similarity, I will give you the definition. I like the name of the definition that was given in the paper by Semenov and Rudin, and Cynthia Rudin has many papers on this topic. And they refer to this movie from Kurosawa that shows, I think it's a crime that you see from different perspectives, and there's no actual truth. Every view on the crime is valid in some sense. So it's to say that you may have different decision functions that are valid with respect to your objective. And so if you fix the level of the empirical risk, there is a range in which, up to some theta, for which all the assumptions, the decision function in the hypothesis class are comparable in this respect, so that their empirical error is smaller or equal. Well, it stands, at the theta interval, size theta, from the minimal, the minimizer of the empirical risk. So what I will present now in the technical part, let's say, of the talk is how we can sample as well as possible within this set. Okay, that's if we want to perform some kind of uncertainty quantification, given, considering all the valid predictors, how well we can cover this Rashomon set. That's more or less the idea. So just before switching to this technical part, just a few comments about the relevance of academic benchmarks. So what I have discussed about this kind of benign overfitting effect on academic benchmarks is still conditioned on the fact that we have similar distributions. Now, how to deal in practice with the sampling bias? Because this is always the case. You know very well that you can train with all the best practice, all the cross-validation, all the test sets you want. When you light on your decision with fresh data, there are always some issues. Okay. So one possibility, and this has been done in some of the popular benchmark, is to kind of open the benchmark and allow to bring new data. Okay, so this is I don't know how much time I have because we started late.
15. We still have until 1:10.
1:10. Okay. Yeah. So I can show you. I don't know if I can switch back to, well, maybe I will not take the risk. We'll see maybe at the end of the talk if I can. But here you have a link to an online journal, which is called Image Processing Online, on which you publish paper, code, and a demo mode. And so you can play the algorithm in the paper on your own data. And then there is an archive that is created with all the experiments that people did. And so you have some kind of, living, it's a living benchmark, basically. It's like you have a living state of the art. It's alive. The state of the art is alive. Because people are submitting data, they are testing your algorithm, and you can see the results. Maybe this is the future of publication in data science if we want, our productions to have some meaning in the real world. But of course, this raises many technical issues. Initially, this journal was devoted to image processing algorithms where you don't even have any learning stage. It's like, one image input, one image output. But, it has some versatility and it can be applied to other information processing problems. And I think this archive that is open is a very interesting feature of the journal. of course, there are some technical scientific responses to this issue with new setups, like domain adaptation, transfer learning, pre-trained models. They kind of, try to cope with the sampling bias. And the big question is whether deep learning methods can extrapolate, so out of distribution. So this is the problem I want to consider now. And this is based on a paper that was produced some years ago, but was published only early this year. So this is joint work with Antoine de Matelin, our PhD student, François de Heger from the company Michelin, and Mathilde Mougeot, who is a colleague of mine at ENS Paris-Saclay. And so what is quite documented in the literature is the fact that if we look at the uncertainty quantification that is provided by an ensemble of deep learning, of a deep learning algorithm, it's kind of over-optimistic on real but also on synthetic data. So like the confidence bands you obtain are very narrow, and so when you look at the ground truth, you're very often out of the limit of the confidence band, and sometimes significantly out of the confidence band. So one of the data sets that have been used in these studies, known as CityCam, so there are video recordings of traffic, and this is video during all day and for different weather conditions, different conditions of traffic. And you see that if you see at the upper right corner, when there is some rain on the camera, of course, it becomes very difficult to analyze the image. And the criterion here is whether you are able to count the number of vehicles. Okay, so humans will have trouble in counting vehicles at the upper left-right image. Okay, so we expect that also the algorithm maybe will have some trouble in this kind of situation. But even on simpler data sets like the NIST data set, if we look at the uncertainty out of distribution, again we have the same kind of phenomenon of overconfidence, and this holds for ensemble-based estimates, but also with Bayesian approaches. Bayesian neural networks with where you penalize the log likelihood by the Kullback-Leibler distance with the Gaussian prior, typically. Then you again have, just to generate more diversity in the weights of the network, then you again have this kind of overconfidence on the behavior of the predictions out of the training data set. And we can see this also on synthetic example, just two-dimensional. So you have a classification example with the two moons on the bottom line, and the regression example with the sum of x plus two sinusoids with different parameters. You can see the cloud of points. This is the training data. You have the true function. And then you can see in blue what is the estimate with a neural network. And the shaded area is the confidence band with the ensemble, where you keep some proportion of your predictors playing with the weights of the network. Okay, so we can see that we have, of course, an excellent fit in distribution and a disastrous fit or very wide confidence bands in the classification case out of distribution. So this is, so the analysis we had was that probably we do not sample very efficiently the Rashomon set of the population of weights that kind of fit the data and at the same time may provide more diversity out of distribution. So there are, of course, several approaches to uncertainty. The most intuitive are the distance-based uncertainty, whether, you know, the new evaluation point is far from the training set. So you can think about various quantities to quantify that. And another approach is closer to what we have done, is the ensemble-based uncertainty. So like generating consistent hypotheses with the training set, and for which we will be able to observe some kind of diversity in out of the training data. So this is another view of, you know, this notion of uncertainty that combines the, let's say, the uncertainty due to the estimation error and to the fact that we are out of the distribution. So here you can see, if you have the input space here, you see the two distribution is how the training data are sampled, and the bands out of the dashed band are the OOD region. Okay, so this is where we would like to have wider confidence bands. So there is this notion of consistent hypothesis. So both are consistent, but and those are on the right-hand side, those fitted with a deep ensemble, and on the left-hand side, those we would like to obtain with some sampling strategy of the weights of the network. So just to illustrate further, but maybe it's clear enough, but if we represent the space of weights, this is the space where we would like to perform this sampling. So each coordinate in this space corresponds to a given network with a given choice of weights. And we have an initial perturbation of the weights that we can reflect here. And in the end, we have the points that in this red cloud, those that have let's say a low training error. So those which are consistent with the training data. So if we look at the deep ensemble behavior, it looks like we don't cover well enough this red area. So we do some selection of weights to build the ensemble, those that are consistent, but probably there are not enough. There is not enough representation of this set. And if we use the Bayesian strategy, there's some kind of very regular transportation of the perturbation of the weights to the domain that corresponds to the consistent functions. So the strategy that was proposed in this paper was to penalize, not with some notion of Kullback-Leibler and some prior, trying to fit some prior distribution, but rather to maximize the entropy of the weights. And the entropy is to be understood in a quite generic expression. So this is how the criterion looks like. So we try to minimize with respect to some parameterization of the set of distribution denoted by, so the parameter is phi, and this is a d-dimensional parameter, and we denote by q phi this encoding of the, so we have a notion of entropy that is minus the expectation with respect to this q phi function of minus log of q phi of w. And the first term is the average empirical loss. And using this formulation with various representation of q phi, we managed to have much wider confidence bands. So the way the algorithm works is that, well, there is some idea of using batches of the training data, but then the key idea, the key ingredient is the reparameterization trick by Kingma and Welling, which takes as a distribution some function omega that depends on phi, but also on a random variable z. So we kind of sample with respect to this random variable. You can think of Gaussian or uniform sampling for Z. And there are various parameterizations of omega. So one is based on linear representation. One is based on some singular value decomposition of the matrix of the that reflects the inner layer of the network. And then you have some kind of tensor product of this SVD representation in the case of multiple layer and fully connected networks. But given this kind of, well, you have some kind of pseudocode here. So sampling with Z, we get this, this functional, and then with the stochastic gradient descent, we calibrate the phi's. Well, we estimate the phi's so that we can then, using the phi's, sample with respect to omega and generate instances of the network with different W's. So here you see a particular and simple case of parameterization of the weight distribution. So this is like you start with a pre-trained deep network. So this is your, it gives you a W bar, and then you will perturbate this W bar according to the Kronecker product of phi and Z, and the Z are sampled with the two distributions I mentioned, and the phi have been estimated by this stochastic gradient descent with the previous algorithm I have just described. So an important thing to mention is that the spread of this distribution of the Q phi is related to the size of the phi square. And interestingly, in some simple cases, so maybe I will skip that. Yes, this is what I want to show. So this can be showed for the linear, in the linear case, just considering a linear regression. We can find with a closed form expression the value of the phi chi, of the phi's, and those phi's, they are inversely proportional to the square of the norm of the xk, which are the input training data. So this, this means that the phi's, they are large when the neuron activation amplitude for the training data is small. So it means that the weights at the input of this neuron, they have, let's say, a small effect on the prediction. But if they are activating in out of distribution, the phi's will kind of boost the value. Okay? So this is the way let's say the red set is better covered with this this optimization strategy. So you have some preliminary results that show that we have, of course, better confidence bands out of distribution, like they make more sense. At the same time, it reduces the prediction power of deep learning. It's like to say what happens out of the domain is, many things can happen actually. Going back to the CityCam data, here you can see the difference between the deep ensemble with this narrow quantification of the uncertainty out of distribution. The training set is the first part. Say we train from 2 p.m. to 2:30 p.m. And then we can see what happens in the afternoon, and then it starts to rain, the traffic is denser. And so the method with the joint, minimization of training error and maximizing the entropy of the weights with this parameterization I introduced gives you more reasonable uncertainty quantification in this part of the domain. There are further experiments that have been done with stronger shifts with respect to the in-distribution data, like we can have camera shift. the fact that we have big buses in the image, it also perturbates the count of vehicles. And then there is a weather shift, you know, if the camera gets wet, then of course the image becomes very hard to decipher from humans and the algorithm as well. There are some statistical performance that has been observed, and the method is particularly strong on this data set. It kind of achieves always best AUC performance and false positive rate at 95% over several repetitions of the experiments. And it has been tested also on different benchmarks, and some have been designed specifically for OOD, for the assessment of OOD algorithms. So, well, you can check the paper if you want to have further details on the way it has been implemented and all the details of the experiments. Just to mention that the technique that is presented here, there are many variations, but the variations perform particularly well on the near OOD setup, and they are less efficient on the far OOD setup. But these are like, you know, expected results. But now I'd like to spend the end of the talk just to discuss the third question I had about the prediction power of all this technique. What does it bring to science and to knowledge in general? And maybe the first discussion to have is about, you know, all these benchmarks are usually aiming at matching the human performance. What does it mean exactly? It's not always clear. If it's just, you know, understanding a visual scene, okay, or handwritten character recognition, we could agree. But now what human performance means in the case of medical diagnosis, then, you know, I've been interacting for about 10 years now with clinicians. There is, you can have a lot of discussion what is, you know, what is a diagnosis, even what is a pathology, and in the context of an aging population, even these notions of pathologies, they are kind of, you know, they have to be probably rethought from the start, because all the nosology, for instance, of neurological diseases was developed in the 19th century, but the population was not getting that old as today. So today, people have cocktails of pathology. So, you know, what does it mean to have, I don't know, a particular syndrome? Usually you have many syndromes at the same time. And then it's also a matter of context, a matter of, well, many things. Solène mentioned before the COMPASS case. The endpoint in this data is the risk of recidivism. That's the decision that is taken to put someone in jail or not, whether the person will appear the day of the court in the court. Again, you know, what are the drivers of this decision? I mean, human performance would be the decision of the judges, maybe, but based on what exactly, you know, if the labeling, I think, can be questioned, because there are many reasons why someone may not appear in court. It can be because the person is a criminal and doesn't want to get, don't want to go to jail and will not go to trial, but it's maybe also due to other constraints that people have. Maybe they need to work, maybe they have kids at home, you know, there are many reasons. And the less favored minorities, maybe they have more of these issues. So this notion of recidivism, just taking into account a label, can be questioned. That's what I think, and what also other people think, and there are papers about that. But the idea of matching this human performance makes these algorithms look like emulators of human capacities, maybe human intelligence. I don't know what this means neither, but anyway. And so there is another line of thought that, you know, the computation architectures may inform on how the biological systems function. And you all know that the initial inspiration for the formal neural network, for the formal neuron, came from biology in the 40s, last century. But how much of that is, let's say, captured by the modern architecture, it's not that clear. And I can give just one argument very quickly, but if we think about our capacity to observe the biological system, how close we can get to the neurons with physical measurements, this is only in lab experiments and in very controlled scenarios. So it means we'll have very small populations, so less capacity to have statistics. And the more, so in this graph, what you see is the lab conditions are at the extreme left, and let's say the natural condition are the extreme right. Okay, so here is people or animals in their living environment, completely free, no constraints. Okay, in everyday life. And here you have lab experiments like you do an MRI. An MRI, usually you are, you know, laying, you're not having any activity or very limited activity. There are some animal experiments on animal models. They can do some kind of, you know, they have some capacity to measure the neurons directly and measure the activity with some simple task like grasping an object, for instance. But grasping an object may involve up to 400 muscles that activate synchronously. And we don't measure this activity, never. Okay, so even very simple tasks like this, grasping an object, we have no capacity of recording what happens in the body. Okay? So there are many things we don't know. That's what I want to say. There are attempts, and in my lab we are trying to work in between, say, having more capacity to record the behavior. Maybe we get far from the neurons, but still we have more information than through a smartphone or a smartwatch. Okay? So this is a very interesting field, the field of behavioral studies, and I think data science can bring a lot to that. But remember that MRI is probably not saying much about how the brain works. And this is essentially, you know, what, you know, top-notch researchers in brain research, they focus on the brain essentially, not that much on the behavior. On behavior, we have very poor methodologies, and I believe that here there can be huge contributions of, you know, all the knowledge we have accumulated as a community. And there are things happening now. So there is a software called Deep Graph Cut or Deep Lab Cut, I don't remember exactly, that monitors the behavior of mice in cages, like 24/7. And it's based on video recording of their activity and encodes immediately the behavior of mice over time. A last idea, if time permits, okay, is trying to move far from this, you know, eternal discussion whether the man will be replaced or whether the algorithm behaves as humans and so on. There is this question of how they may interact. And I don't think this should rely on any biological analogy. It's just a matter of safety. So transportation, when we talk about safety, is of course a good example. And we have worked on some experiments in transportation with the drivers of TGV, but also with pilots of helicopter pilots. And I think we all agree that automatization brings more safety to systems, right? Does someone disagree with that? Well, with time, you know, maybe the first one not that safe, but with time it gets safer and safer. Okay, if you take the metro, you know, now that we have automatic lines with, you know, I believe they are safer than before. But this is a general statement, but well, you can disagree, but I think most of the people would agree. And then there's another statement that says that, well, when it gets messy, it's better to have a human operator. Would you agree with that? Well, driverless cars, you know, 7, 8 years ago, everybody thought that they would happen, but they are not happening. Would you get into a plane with no pilot? Who would get in a plane with no pilot? Nobody. You're wrong. There are planes, you know, with no pilots. There are drones. There are even Boeing big planes, you know, with no pilots right now, with for courier mainly. But they are operating very safely. But the two together, it may be an issue because you have to deal with a transition from the automated mode to the human mode. Okay, and there, nobody studied what are the biological limits of a human in an extreme scenario who is disconnected from the context, because there is the, you know, the automatic part that is doing the job, so the operator may be sleeping. What is the capacity of a human to take control? It's well known from people in ergonomics. But ergonomics is a discipline that belongs to psychology, at least in France. So the academic section is under the section of psychology. So there's no data science. It's very qualitative. You know, no measurements, no nothing. No hard science as we know it, as we practice it in all this stuff I have discussed before. So tracking the biological failures is a major scientific issue. And I think data science can contribute to that. And then there are the organizational biases. If you look more globally at the level of our organization, and so we'll have the answer to Hinton now, and I will finish on this slide. So there's a team of behavioral economists from MIT. So it was end of 23, and it's still, I think, a preprint on NBER, so National Bureau of Economic Research. We have lots of preprints from colleagues in economics. And the title is Combining Human Expertise with Artificial Intelligence, Experimental Evidence from Radiology. And the paper starts with a quote, which is Hinton's quote. So it's like the answer to Hinton's quote, like, we don't need radiologists anymore. It's, you know, we have enough, algorithms will arrive and they will do their job. And it's very interesting, this paper. And it's not, you know, just a discussion paper. They actually did a field experiment with more than 200 radiologists, more than 200,000 X-ray data. So we're talking about serious stuff, you know, like experimental evidence. They used neural network that was trained on data that were labeled by 5 top radiologists from very famous American hospitals. Like they had the super AI tool. And then they said, let's check who is the best. And what they did was to compare clinician performance with no assistance, the algorithm, no human assistance, and then a combination of the two. And what they found was, I think, extremely interesting, because I think it raises a new research question. Yes?
So the 5 top-level specialists are the ground truth here?
Yes. Well, you can imagine, you know, the biases that occur, but anyway, I think it's still interesting to look at this. Of course, we can have an analysis that, of course, would explain, you know, the results, but I think at their level, it's interesting to see what they observed. is that, first of all, if we provide the AI predictions, it doesn't mean we uniformly increase the diagnosis quality. And if we provide contextual information, then it increases quality. Okay? And if we just do the benchmark, oh, the sentence is cut here, but what it says is that the optimal solution typically involves delegating either to human or to the computer, but not to the clinician using the computer. Okay? So it means that it's obviously context dependent, and probably there's something we have not understood on how, you know, a human expert deals with the information that comes out of an algorithm. So there's something to understand there, I think. So maybe there are these issues with biases, but it's also related probably, that's why I think it's strange, for me at the beginning it was strange to see that there were teams of economists that were working on this topic, but then I understood is that you need to have this kind of holistic approach on the whole system. Technology is just a part of the organization, but you have to understand all the biases that come from, you know, how the hospital works, basically. And there are other papers that kind of highlight, you know, positive effects of technology, but probably it's not by training AI with the top clinicians in the world, you know. It's probably not the solution. And I will stop here. Thank you.